but bonsais are expensive.
Yeah,
So
but like bonsai in the middle sounds right though.
it does. I kind of like. I wonder if we can get like a fake bonsai.
I mean, they gotta make fake bonsais.
They have to. Somebody somewhere
Has made a fake bonsai.
somebody somewhere has made a fake bonsai. I wonder if we could 3D print a bonsai.
I mean, well, it look like it's 3D printed, but yeah, I mean,
like,
sure, yeah.
maybe it's a digital
I guess
bonsai.
that's
I don't know.
on topic, but like if we're going, I don't know that that's going to read as much to the two ferns thing, the between two ferns thing.
You're probably right.
But yeah, like
bonsai in the middle, though, I feel like it's a good vibe.
That's a good vibe. It's better than shrub in the middle.
Yeah.
Or bush in the middle, or any number of other terrible.
Yeah.
Like
shrubberies in the middle. No.
Yeah, no. Bonsai in the middle. I like it. So we'll search for one of those.
Yeah.
Well, welcome everybody.
Well, welcome to Statics.
that was your cold open here.
Yeah. Let's get back on the actual correct. The correct slide.
The title slide.
The title slide.
We're jumping straight into things. Nope. So, yeah. I think that was a good lighthearted way to get into trigonometry.
Talking about bonsais?
Yeah, talking about bonsais. Isn't there a ratio that's involved in triangles in regards to how you trim a bonsai?
I think so. There's definitely some aspects of like there's some math that goes into like the correct proportions for certain bonsai arrangements.
Yeah.
I'm not familiar with them though, but
they've got to be encased in the Fibonacci sequence, which is therefore tied to trigonometry.
That's our story. We're sticking to it.
We're gonna stick to that. Yeah.
Yeah. That's how
it may be wrong, but we're sticking to it.
Yeah. Anyways.
So today, you're in for a treat. We're going to be talking about trigonometry, which is something I know you've dreamed about since childhood.
Yeah. Everybody is just like waiting on pins and needles to have this conversation about trigonometry.
It is, it is the biggest anticipation that you've got in your entire academic career, I'm sure.
Learning trig.
Learning trig, yeah. But trigonometry, like spoiler alert, is actually way easier.
Yeah, it's easier when you have things to work with.
Yeah. The problem is if you learn it in just a math class and don't ever apply it to anything in the real world.
It makes no sense.
It makes no sense. Why the hell am I doing this?
Yeah, like what is this for?
Yeah.
Why should I bother to learn this? Well, we will give you the application.
Yeah.
And why you need to know it.
Because you're going to need it
Yeah.
to do the things that you're going to do this quarter.
Yeah.
So trigonometry is stuck here. It doesn't just exist in the mechanical systems class.
It exists in the panel systems class or
the panel
build.
systems, and it'll exist in motion control much later on.
Yeah. Trigonometry is the superpower math. You can do almost anything with trigonometry.
You can, and it's because almost anything that exists in the physical world can be broken down into a series of triangles.
Yeah.
And that's if you think about your 3D printed files, right?
Yeah.
When you make an STL file, that is
literally a mesh of triangles.
a bunch of triangles.
That's all it is. When you're looking at anytime that you're looking at like any form of vector graphics, triangles.
Triangles.
Like
Triangles are how your graphics processor actually works.
Yeah, like at the fundamental level, it's generating triangles and it's doing lots of triangle math.
Yeah. And so trigonometry is the study of triangles.
Yeah.
And the study of how to measure triangles. Actually, that's where the root word comes from.
That's where the metry in that word comes from.
Yeah, so we're measuring things, right?
Yeah.
We're measuring the angles of triangles, we're measuring the lengths of the sides of triangles, and that's really all we're doing. And it's not as bad as anything, but you've got to come around to a certain amount of the vocabulary involved in it.
Yeah.
The calculations that are involved in this should be done with your calculator.
Do not do them by hand.
Do not do them by hand. Do not look them up on a table.
Yeah, no.
Do not get a slide rule, because slide rules don't exist.
Yeah, we have this thing. It's called smartphone. But you can use it if you want to be old school. You can use a dedicated calculator.
Oh yeah. Here we can do like neat things that you probably didn't realize with your smartphone.
Right.
Hang on a second. I'm going to pull up my calculator here on my smartphone. If I look at it this way, right, I just get the addition, subtraction, division,
Yeah.
you know, multiplication, right? Check this out. I'm going to take this and I'm going to flip it like that.
It didn't change.
It didn't change?
Didn't change. Do you have your screen locked?
I might have my screen locked.
We might be old men right now. The point is that your calculator and your smartphone.
Can you do this with yours?
Maybe. Who knows? There we go. This is what he is essentially trying to point you guys at.
Yeah, I have my screen locked so it doesn't change positions.
Yeah. Do that on both cameras. You'll notice that there are a number of functions there that we can use to do all kinds of fancy math. Most of them are dedicated to working with triangles.
Yeah.
And so that's why we use a modern calculator.
Yeah.
If you want to be old school, you can buy a dedicated one, but you can get a perfectly serviceable one out of your smartphone.
Or you can use one on a desktop computer or on your laptop or whatever. But there's always
Yeah.
the thing is that like back in my day they lied to us. They'd say you're not always going to have a calculator on you, so you need to figure out how to do calculations.
Lo and behold,
they lied.
yeah.
I got a calculator on me at all times.
At the end of the day, though, the reason, like when it comes to this discussion of trigonometry,
Yeah.
it is probably the most useful math that exists from an everyday perspective. And if you're in any of the STEM fields, I do not care which one it is, you will use trigonometry all of the time.
You should use a trigonometry when you're building a deck, when
Yeah.
you're doing any sort of construction work. There's no better way than the 3-4-5 rule to do a right angle, to verify a right angle.
That's absolutely true. We should talk about the 3-4-5 rule at some point.
It will come up.
Guaranteed it will come up.
Yes.
It's a triangle.
It's a triangle. It's a type of triangle.
Yeah.
All right, let's move on to the
All
next
right,
slide here.
next slide. We've talked enough about. All right. Yeah.
This and that.
And
So this falls broadly under the category of statics, and so we need to kind of talk about that a little bit here.
yeah.
Statics is kind of a continuation of mechanical systems. The golden rule still applies. Whatever you gain in power is lost in distance, et cetera, et cetera. What you gain in distance is lost in power. And so mechanical advantage still applies. So basically you can have a measure of force that's amplified through an angle. And the angles are where we get into the trig.
Yeah. When we start looking at angles, you start dealing with triangles.
Yeah.
When you get to triangles, you're dealing with trig. That's just
Pretty much what it is.
that's just how it works.
Go ahead.
So,
So the reason why we call statics is because everything is held still. And this is an important thing because if we're going to draw a triangle, we don't want to draw a triangle and then what that triangle looks like 6 seconds from now,
yeah, we want to draw one triangle. We don't want to draw a million triangles.
which is what separates
Statics
which is trigonometry,
from dynamics,
from dynamics, which is calculus. So an important thing to note here as a context, when we're talking about things, these systems need to be in static equilibrium with their environment. And it's an important thing because it's all about the context.
Yeah.
Obviously, in this room, my hand's moving, but my body's not really.
Right.
My body is static.
The chair is not moving. The table is
sitting-
not moving.
Yeah, right. Things are not moving
Yeah.
relative to this space here.
We assume that the objects that we're dealing with are not moving.
Right. And so, when we deal with a statics problem, it's always within the context of what its environment is.
Yeah.
You could be on an airplane, and you could have something that is in static equilibrium
With the airplane.
with the airplane, but it's not in static equilibrium with the ground because it's moving.
Exactly.
Or in the car, or on a train, on a boat, whatever.
The explicit example here is that you are sitting in a chair on an airplane. The airplane and the chair are moving together across the Earth, but they are in static equilibrium with each other.
With each other, yes.
So the chair is not moving through the aeroplane.
Yeah.
Ideally.
And right now we're moving at several thousand
yeah,
miles an hour because we're orbiting the sun at a very distinct velocity, and the sun is orbiting the galaxy at a very distinct velocity.
And our entire solar system is moving through the galaxy and through the universe, or excuse me, our entire galaxy is moving through the universe
at another velocity. So like, I mean, this is what relativity is, right?
Yeah.
It's all relative.
It's all relative. But with statics, we are taking a particular frame of reference, and we are saying that the things inside of this frame of reference are in static equilibrium with each other.
They don't move.
They don't move relative to each other.
Relative to each other, yes. All right. So when we talk about this, and we'll get deeper as we go into this on net forces and moments acting on a system, but the definition of equilibrium, where it isn't moving with regards to it, is that the sum of all forces and all moments. Moment is a force that is turning rather than a linear force.
Right.
We'll get more into that, but those sum up to equal zero, which makes our equations kind of nice.
Yeah, it's kind of
because the answer to all of it is zero.
Yeah, it's kind of like when I first made this connection, is because I had just taken an electronics course prior to my statics course. And the connection that I made is that just like in an electrical circuit, all of your currents must, or all of your voltage drops in a series circuit must sum to zero. All of your forces in a static system must also sum to zero.
Yeah.
So that's for those of you that are just coming off of a bender on electronics, perhaps.
Yeah.
That's an easy way to conceptualize what's happening here.
Yeah. All right, so let's hit the next slide here. So, a book, your phone, whatever's sitting on your desk, on a bookshelf or whatever, is an example of static equilibrium. It's not moving with regards to its environment. And it really comes down to velocity, right? If velocity is constant. If it's accelerating, like if you're in a car,
that's changing in speed,
then it's not static.
Then you're not static. And you can tell
velocity has to remain constant.
Yeah.
In order for that to happen. So if and this is why things go all to pieces when you've got turbulence on an airplane, right? Or you've got on a boat when you've got a massive amount of rocking, all of those static assumptions go out the window.
Because the frame of reference fundamentally is changing.
Because velocity is fluctuating.
Yeah.
As long as we are remaining constant in velocity, we can have static equilibrium. If we're accelerating or decelerating, like you're in the car and you're getting thrown forward, then the system becomes necessarily dynamic.
Yeah. There we go.
So, sum it all up, we're talking about equilibrium when we deal with statics. All right, hit the next slide here. This is where we get into triangles. So everybody should be familiar with what a triangle is, hopefully. But you may not be as keen on some of these triangles. We've got our right triangle, which is a triangle that has a right angle in it. Mm-hmm. And then you have oblique triangles. So of those, you've got the obtuse triangle, where one of the angles is greater than 90 degrees. Or you have an acute triangle. Acute triangle means that they're all acute angles in that, which means that they're less than 90 degrees.
Yeah, so all of the angles a triangle has will be less than 90.
Acute means less than 90 degrees. Obtuse means greater than 90. Now, notice that an obtuse triangle still has two angles in it
that are acute.
It's just that one angle, and that's going to be the case. You make any angle of a triangle
greater than 90.
You
have an obtuse triangle.
You have an obtuse triangle. Because if you look at the last little bullet point there, triangles are kind of neat. The sum of all the angles equals 180 degrees.
Always.
Always.
There cannot be a triangle that has more than 180 degrees.
It will not work. It will not close back in on itself.
It is an impossibility.
Yep. So that means that if any triangle has greater than 90 degrees, you can't have another angle in there that is greater than 90 degrees as well. So it's going
because therefore, because it will adhere to that 180 degree rule. And like the thing here when we're talking about a triangle, it's important to keep in mind that a triangle is a closed shape always. If it's open, it is not a triangle.
No.
And that's why we say it's like you cannot have a triangle that exceeds 180 degrees in the sum of its angles.
Yes. Yeah. And so from this, we can gain a little bit of knowledge here, and there's some basics of math that you're probably really familiar with here, but if you know two angles of a triangle,
mm-hmm.
you know the third.
By definition.
By definition, you just have to subtract the other two from 180. Simple. The other thing that we can talk about here as well is Pythagorean theorem.
Yeah.
Right? And that deals with the lengths of the sides, right?
Which is, I think, where a lot of people have their first traumatic experience with triangles and trigonometry, is that they were taught this in an impractical way.
Yeah. And a squared but plus b squared equals c squared is the Pythagorean theorem. You will use it.
You will use it. You will use it in this class. You will use it in your other classes.
You will use it for good. You may on your own
use it for evil. We will neither confirm nor deny our own experiences with that.
Yeah. But it is unavoidable. You will be using Pythagorean theorem, but you'll understand why you're using it a lot more here because we will have the context.
Yes, it's not going to exist in just a space, a hypothetical space. We will have practical applications for it.
Actually, back up. One thing here. I want to point out though, if you have an oblique triangle, you can turn either an oblique or an acute triangle into two right triangles by drawing a line from one vertices to the base
of the other
side.
Of the other side.
So if we went from the angle there that's greater than 90 degrees across to that hypotenuse.
Yeah. The hypotenuse is the longest edge on that angle, on that triangle.
Yeah. That would become two right triangles.
Yeah.
So that's an important tool that we're going to do when we're dealing with triangles. We're going to take anything that's oblique or acute, and we're going to turn it
into two right triangles. And then we are going to use maths to compute important relationships among, for various applications.
Because you need to use a right triangle if you're going to use Pythagorean theorem, and you need to use a right triangle if you're going to use any of the trigonometric functions. So now we can move on to the next slide because we can deal with all triangles as if they're right triangles just by splitting them up.
Yes.
Just by subdividing.
And just as a side note, when you see really advanced, another application of trigonometry here that people think is really overly complex is machine vision that does spatial analysis. That's all just what we just talked about. Mm-hmm. Is literally taking angles, figuring out the triangle, splitting that triangle in two, and then running Pythagorean's theorem on there to figure out distances and spatial relationships between what can be seen inside of the angle of a camera.
Yeah.
It is no more complex than that at the end of the day.
Yeah. So, I mean, and then, so let's get to the heart of it. The hard thing, right?
Yeah.
Is this. Sine, cosine, and tangent.
This is literally all of trigonometry. At the end of the day.
We're done. I'm going on break.
Yeah. Okay, we're done. Study this slide. We'll come back.
We'll come back. No. So this is a right triangle, and then it's important to note the labeled things on this. Right. The Greek sine theta there, that is the angle that we're looking at in degrees. It could also be in radians. An important thing to note, when you're using your calculator, set it to degrees if you're working with degrees. If you're using with radians,
set it to radians. You will get different results. It's really important that you understand what you need.
Yeah.
We'll get into the context of that.
We'll get into the context of that, but most of the time you'll be working in degrees.
Yeah, probably 9 times out of 10.
This right here, that theta is the angle in question, right? And so everything is, how we label the other sides of the triangle is kind of in reference to that theta. The hypotenuse is always the hypotenuse. The hypotenuse is the c squared. It's the longest one.
Yeah, it's the longest edge on a right triangle.
On a right triangle. And then adjacent and opposite depend on the perspective of what angle you're measuring from.
Right, so if we're measuring in the lower left-hand corner of this triangle that's currently labeled theta, adjacent is going to be that long straight edge.
Yeah.
And opposite is going to, like, the angle points across. You just draw a straight line.
It is opposite the angle.
That's where it comes from.
That's why it's called. Adjacent means close to. Opposite means away from.
That's how you get the name. So if we change our point of reference and theta is now, or the angle is now in the upper right of this triangle, our adjacent is the vertical line and our opposite is the horizontal line.
Yes.
In case anybody was unclear about what we meant by that.
So sine of theta is essentially a function that delivers you the ratio of the opposite to the hypotenuse.
Yes.
And that may sound more complex than it actually is.
It's literally taking like the proportional lengths of each one of them and dividing them against each other, and you get a number that is a percentage out effectively of what it is.
Right. So you have sine, cosine, and tangent. You also have cosecant, secant, and cotangent, which are just inverses of those three respectively. But sine equals the opposite over the hypotenuse.
Cosine is the adjacent over the hypotenuse.
And tangent is the opposite over the adjacent. So what this means is, using these functions mathematically, if I know the angle and one of the sides,
we can determine the other two.
We can determine all the angles and all of the sides.
Yeah.
And if I know two of the sides, I can figure out all of the angles. I can figure out one angle and then I'll know all of the angles. And I can figure out that other side.
Yeah.
So
you can characterize the entirety of the triangle
with very little information.
Yeah.
Very little information. And that's what makes it so powerful to divide these things up, because things that we don't have dimensions for, things that we don't know or not given, we can ascertain mathematically.
To a very precise degree.
Yes.
Like we can, and this is again why we say trigonometry is kind of like the most powerful kind of form of math from a practical perspective, because like you can literally solve almost anything with it.
Yes.
I'm sure there are exceptions to the rule here.
Yeah.
But I haven't personally ran into a problem I couldn't figure out with trigonometry if I really needed to.
Yeah. And the thing is that, okay, how do I memorize this? How do we do that?
We memorize a chant.
There's a chant.
Yeah.
It's a chant.
So, ka, toa.
Yeah. So, ka, toa, so, ka, toa, so, ka, toa, so, ka, toa, so, ka. Hopefully you'll have terrible nightmares about us talking about that. But that is it. That chant is how you remember that, because so is sine equals opposite over hypotenuse. Ka, C-A-H. Cosine equals adjacent over hypotenuse. Toa.
Toa is T-O-A. Tangent equals opposite over adjacent.
All you need to know. Now, hopefully, you've got this slide right here committed to your memory, and you'll be able to move forward with it.
Memorize this.
SOHCAHTOA. SOHCAHTOA.
Just remember SOHCAHTOA and relate it to these three.
The other ones, cosecant, secant, and cotangent, are much more...
they're optimizations.
They're optimizations.
For doing for running certain formulas and for doing certain things to make getting to an answer faster.
And it was more for when you were doing it by hand.
Yeah.
You will rarely use those.
Yes.
Now that you've got a calculator.
If you have a calculator, I struggle to think of when there would be a major advantage to use cosecant, secant, or cotangent.
Yeah.
Like, there's not. It's an optimization for when you had to do this by longhand primarily.
Yeah.
Depending on if you're looking at older reference material for how to determine.
You may need to look this up and remember it.
Yeah.
But the only one that you need to remember is the sine, cosine, and tangent.
Yeah. SOHCAHTOA is really important. We do expect you guys to remember that stuff.
Yeah.
So, learn the chant.
Learn the
SOHCAHTOA. SOHCAHTOA. Anything else on this slide?
I think that's good.
Okay. Yeah. Oh, having a little bit of delay. There we go.
Okay. Where are we at on time?
26.
Let's call it good for this video. We're going to do the forces in the next video.
Okay. Sounds good.